Hi there, this is Mrs. Ortiz, and I'm going to cover the geometric mean theorems and explain the actual theorems and where they come from. In a separate video for Mrs. Keys, you can find the examples. And I have with me Cooper, who wants to say hi.
Hi.
And Evan, who's making squeaky noises in the background, who probably also wants to say hi. Evan, do you want to say hi?
Yeah.
Say hi.
Hi.
All right, and we're gonna get to it. Okay, so for the review questions, find the geometric mean, number 1 and number 2. I am going to let you refer to your geometric mean notes for doing that. And then number 3, take a look at those, and you can determine that the triangles are similar by AA. So that's just to get started, but you can refer to older lessons if you need more detail on that. So I'm going to start with number 4, and it says, write a similarity statement identifying the 3 similar triangles in the figure. Explain why all triangles are similar to each other. So if we take a look at these triangles, something that's missing and important on this is that angle B is a right angle. So that should not have been omitted. Sorry about that. But if we take a look at all 3 of these triangles, let's look at triangle ABC. Okay, so it has a right angle. And then let's take a look at triangle BDA. And let's draw it in red in the same orientation as ABC. So it's got a short leg, a longer leg, and a hypotenuse. And if we match this up, the right angle is vertex D, and then it goes to the short leg A and a long leg B, or a hypotenuse of AB. And then let's take a look at this triangle right here. We'll call this the medium triangle, triangle BDC, and let's go ahead and put it in the same orientation as the other 2. And again, we want to identify the right angle. Well, the right angle is right here with a vertex of D, and the short leg goes up to B, and then that connects and leaves C, okay? So the question is, it says, write a similarity statement identifying the 3 similar triangles in the figure and explain why all the triangles are similar to each other. So the question is, are they similar? So if we look at the big blue triangle and the little red triangle, we know that they both have these right angles, right? So there's one pair of angles, but they also both share this angle A by the reflexive property, right? So these 2 triangles are similar by AA. And then similarly, if we do the same thing with the medium-sized triangle and the big triangle, we know that they both have a right angle, and then they have a reflexive angle of C. Okay, so here, so those 2 triangles are similar by AA. So these 2 are similar. Okay, so if the big one and the little one will be similar, and the big one and the medium one are going to be similar, then so too is the little one and the medium one. So now we can write our similarity statement, which is going to say that triangle ABC is similar to triangle, and remember the order matters, ADB. That's supposed to be a triangle, whoops. And that's similar to triangle BDC. And this is all by AA similarity. Okay, so as it turns out, this line that's causing these right triangles to all be similar to one another is a very specific line, and it's called the altitude. So let's take a look at what an altitude is real quickly. So the altitude is the perpendicular segment, so the perpendicular from one vertex of a triangle to the opposite side, or the line containing the opposite side. And I'll explain what I mean by that in just a second, okay? So like I said, this line right here, this BD in triangle ABC, is a very specific line. It is the altitude that goes from the right angle to the hypotenuse, which makes those three triangles similar, okay? So the altitude is a line that's perpendicular. It goes from a vertex. So let's look at this one. So from a vertex, and is perpendicular to the opposite side. So in this triangle, if we're identifying an altitude, it is BD. BD is an altitude. But for the sake of kind of covering altitudes completely comprehensively, if this is a right angle, it's not the only altitude. So every vertex has an altitude. So if I'm going from vertex A and need to be perpendicular to the segment BC, okay, how do I do that? How do I do that? What segment do I draw from this point and to be perpendicular to BC? And the answer is, if that's a right angle, is the leg AB. Okay, so AB is an altitude. And we can do the same thing with C, right? If we're starting at vertex C and we need to be perpendicular to AB, to do that, we go down the leg of the triangle and find that BC is also an altitude. Okay? All right. So that's what happens in a right triangle if it's obtuse. All right, this is a little bit interesting, but to go from W and to be perpendicular to the side X, Y, we can't draw a line over here that becomes perpendicular, right? None of those are perpendicular. So instead, what we have to do is we have to extend this side, X, Y, and go from W and go outside of the triangle to be perpendicular. Okay, so what if we want to go from vertex Y and be perpendicular to WX? We can just draw that one. That one's actually internal. But what about if we want to go from X and we need to be perpendicular to the side WY? Well, that's not going to work inside the triangle again. So again, this one comes outside of the triangle to be perpendicular. Okay, so there you have it. So WZ, we can call this YU, and let's call this one, where are we at? I don't know, RST, sure, XT, are altitudes. And obviously I threw in some extras there, but I wanted you to see how they work, okay? All right, so back to the idea, so that's what an altitude is, and back to the idea of focusing on this line being an altitude in order to create three similar triangles, these three similar triangles. That is going to be the key we're doing next, okay? So the first theorem is, it says if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and each other, okay? So that was like using this picture right here, okay? And saying if BD is an altitude drawn to the hypotenuse, then it creates these similar triangles that are triangle ABC, which is similar to triangle BDC, which is similar to triangle ADB. Okay, so what's going to come next is this theorem, but before we get there, I want to jump down and take a look at the examples 7 and 8. So 7 is a mixed up version of this triangle again, so it's slightly different, but I'm going to take a look at 8, and then I will go back to that theorem here in just a minute. Okay, so if you can use 8 and draw three similar triangles, then that will be one way to solve the problems that Mrs. Keys has in her video. Okay, so we're looking for three similar triangles by writing an extended similarity statement. So the first triangle is going to be the like the big one, right? That contains everything, which is, we'll just call triangle RST. And then that's going to be similar to. So then I like to draw a little triangle in a similar orientation. So my right angle is at the top, and my hypotenuse across the bottom. And my hypotenuse is going to be opposite my right angle, so that will be RS, and R is going to be the vertex on the short side. Oops. Here, the hypotenuse, RS, and then it has a right angle of W. And usually I start with the right angle. That makes things a little bit more straightforward in my mind, but it's up to you. So RST, so we're going to go RWS, and then that is going to be similar to triangle. We need to take a look at the middle triangle, and we're going to rotate it so it's in the same orientation again. So let's give it a right angle here. Ooh, that's a little rough. And we know that right angle is W, and the short leg is W to S, and then S to T. And so then we've got RST is similar to SWT. And there's your extended similarity statement for those three triangles, okay? So this idea of these triangles being similar, if we go back up here, it says we know that triangle ADB and triangle BDC are similar by AA, okay? So these two are more indirect, but we've got ADB. Oops, I need a pen. So we know triangle ADB, is similar to triangle BDC by AA. Now, what comes next is important for coming up with this theorem down here. It says use the proportional sides of similar triangles to write a proportion that is a geometric mean. So remember that if two triangles are similar, then their corresponding sides are proportional. This asks specifically for a proportion that is a geometric mean, a proportion that is a geometric mean. So if you remember, like if you have 4 and 12 and you're writing the geometric mean, we were calling it x in the previous lesson, right? So it was like 4 over x equals x over 12. So these two spots for x, they are replicated and they're also in the means position. So then these two spots we called the extremes, okay? So if we're looking for a proportion that is a geometric mean, that means that in two spots of our proportion, we need to have the same thing, okay? So if we look at our two similar triangles, we're looking for the same side that's used twice. So over here, we've got segment BD, and here we have segment BD. So that means if I've got BD in each triangle, I'm going to let those be the geometric mean. Now, I usually like to go left to right or small to big. So if I want to go small triangle over BD, what corresponds there? So DA here corresponds to DB here, right? So I'm going to put an AD in for that. And then we've got BD on the little triangle, which is going to correspond to CD on the middle triangle. And that right there is a proportion, okay, by using corresponding sides, and it is also a geometric mean because these two numbers are, or those two segments are the same, okay? So what I want to do is think about, so this is these two triangles, right? It's these two triangles right here, rewritten. They're just redrawn in a similar orientation. So I want to think about if we put them back together on this triangle right here, what we are looking at. All right, so let's take a look at that proportion closely to this figure right here, okay? So the proportion that we just had was, sorry, that erasing is bothering me. AD over dB is equal to dB over DC. So if we break down the parts of this, AD is this piece right here, and that is part of the hypotenuse. And then we've got dB, which is the altitude. And remember, it shows up twice because it is a geometric mean, okay? So let's put that. So the altitude is the geometric mean of AD, which was part of the hypotenuse, and then DC, which is the remaining part of the hypotenuse. So if I call this hypotenuse part 1 and hypotenuse part 2, okay, I can understand that my geometric mean is the altitude and that it is equal to the hypotenuse of part 1 over the altitude, and that's equal to altitude over the hypotenuse of part 2. Okay, and it doesn't matter which part of the hypotenuse you call 1 or 2, it's just that they are different from each other, okay? So again, one more time, just as a quick recap, AD over dB is equal to dB over DC is the proportion that we are using, okay? Now it's specific for those vertices names, but you can apply it to any triangle. All right, so then we've got another set of these, and we go through these two triangles, and it says we know that these two triangles are similar. This is again by AA, so we can say triangle ABC is similar to triangle, so triangle ABC is similar to triangle BDC by angle-angle similarity. And then it says use the proportional sides again to write a proportion as a geometric mean. So let's take a look at this. We're looking for the side that repeats twice, and I see that BC shows up 2 times. Okay, so I'm going to put BC in as my geometric mean. And then I've got, so what over BC? So what corresponds to this BC? And that would be CD. So CD over BC is equal to, and then what corresponds to this BC? BC over AC. All right, so if we put all of that back together on the next page where we're looking at the whole thing together, we're going to look and see what parts of the original triangle give us this proportion, which is a geometric mean proportion. So let's take a look at that. Okay, so if we go over here, we can recall that it was CD over BC is equal to BC over AC. And let's take a look. So this time BC, which is our geometric mean, is actually a leg of the original right triangle. So we're going to put this over a leg, and that's equal to a leg over. Okay, and then we know that CD is the part of the hypotenuse that is adjacent to the leg, meaning that this part of the hypotenuse actually touches the leg. So this is the hypotenuse, but it is the adjacent portion. Okay, and then the other thing that we have is AC, which is the whole length of the hypotenuse. Okay, so that is the whole length here, and that is the whole hypotenuse. All right, and that's going to give us our second theorem. So it says the geometric mean theorem for a leg is in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. The length of the leg is the geometric mean of the lengths of the adjacent part of the hypotenuse and the entire hypotenuse. Okay, so again, just to make that a little bit larger and a little bit more clear, this is the leg is the the leg is the geometric mean, so BC. And then in the extremes position, we put the part of the hypotenuse that touches and the whole hypotenuse. Okay, so it's a portion of the adjacent hypotenuse over the leg equals the leg over the whole hypotenuse. Okay, now if we go back here, we just have, what this is going to do is this is going to look at leg AB, because there are two legs in a right triangle. And we're going to be able to say that yes, indeed, because these two triangles are similar, that leg can also be a geometric mean. So I am proposing from here that it will be true that AB will be a geometric mean. Not there, goodness, sorry. So AB will be a geometric mean of this part that touches it, AD, and the whole hypotenuse, AC. So now let's look and see. We know our two triangles are similar by AA, so ABC is similar to ADB. Okay, and if that's true, then we have corresponding parts that are proportional, corresponding sides. So it says AD over AB, those correspond, that looks good, equals AB over AC, and those also correspond. So yes, this is a valid proportion. It is also a geometric mean, and it is the other geometric mean that you can have using the other leg. So AD over AB equals AB over AC. All right, there you have it. Geometric mean theorems. I hope you have a great day. Bye.